Hello students, here's lesson 9, sampling distribution. The sampling distribution is the distribution of values of sample statistics obtained from repeated sampling. Repeated sampling. It can be a bit confusing because sampling itself is many times a repetition. For example, how do we get a sample of 200 people out of a certain list? Well, we select a person, another person like that. 200, and that's one sample. And then we repeat the sampling of 200 many times, so we end up with a repetition of repetition. So it can be a bit confusing, and I'm going to take care of that with some example problems coming shortly, but please beware of that computation, or beware of that confusion, or possible confusion. Now, the properties of the sampling distribution depend upon the types of sample statistics, of course. And they are sums, means, standard deviations, ranges, and so on and so forth. But by far the most important for our purpose here is the means. The sampling distribution of sample means. And that's what we're going to do in section 2, 3, and also 4. Now, let's beware of that repetition that I warned you about. And here is an example that discusses that very issue, which may lead to possible confusion. The following program simulates 20 rolls of a fair die repeated 100 times. This repetition yields 100 means of 20 rolls of the die. What do you mean by that? Roll 20 times and we get the average. The first average. Another 20 times and we get the second average. Another 20 times and I get the third average, and that's being repeated how many times? 100 times. So we are talking about 100 means. Mean 1, mean 2, mean 3, mean 4, mean 100. And then out of that 100 means, we can consider the mean and the standard deviation of those means. So mean of means and the standard deviation of those means. Confusing? Yeah, quite possible. And those are represented in blue here. Now, how do they differ from just 2,000 individual rolls? Just take the average of them all. Well, if you look at the means, as you can see here, they're the same. So mean of means versus mean of individuals. Now this program is randomized, so let me run it again. And simulated run yielded the means like that. Whether I take average of 20, another average of 20, another average of 20, and then get 100 of those, and then take the average again and get mean of means, or just go ahead and add them all up 2,000 times and then average up. Either way, I get the same result. But then again, if you look at the standard deviation, they are drastically different. What's happening here? In first 20 rolls, there are some exceptionally high rolls and exceptionally low rolls, and they kind of even out. And that generates a mean. And that mean is being repeated 100 times. So we have more concentration toward the mean and less spread if you take standard deviation of the means. All right? We're talking about 100 repetition of 20 rolls, and 20 rolls will give me a mean, and then second mean, third mean, and then we have 100th mean. So we have that 100 averages, and with that 100 averages, let's consider the standard deviation of those 100 numbers. And that's this simulated number. And then this one is just the standard deviation coming from 2,000 individual rolls. So consider just without grouping at all, just 2,000, and then calculate the standard deviation there. And then the simulated exercise, the simulated experiment, gives you two very different values. And then, this program is randomized, so you get a little bit different results. But each time I run, mean of means versus mean of individuals are the same. But the standard deviation of means and the standard deviation of individuals are very, very different. And then how do they differ? The standard deviation of sample means is much smaller than the standard deviation of the individuals. And why? I think I explained to you before. Each time I take the mean of 20, and exceptionally large and exceptionally low are kind of evened out by taking the averages, and we have less spread. By the way, these are not one is less than the other. It turns out they can be quantified. So here is a theoretical mean or probability mean. We are simulating a roll of dice, so add up 1 through 6 and divide by 6, so 3.5. And as you can see, pretty close to 3.5. And each time I run it, I get different number, but pretty close to 3.5. All right? Now, how about the standard deviation? This is the probability standard deviation of rolling one die. So 1 minus mean squared, 2 minus mean squared, 3 minus mean squared. So each deviation squared and divide by 6. If I do 6 minus 1, that's sample standard deviation, but this is probability standard deviation. So just 6. And what do you get? 1.707 something. And that's pretty close to the standard deviation of individuals. Let's run it again. And do we get something close to 1.707 each time I run? Yes, indeed. Give or take a little bit, but that's where these numbers are hovering around. Now, how about the standard deviation of those samples of 20? So that is standard deviation of the means. Curiously, that's pretty close to the standard deviation, this individual standard deviation, divided by square root of 20. And what is 20? Mean of 20, and then we are repeating 100 times. And this 100 times or 1,000 times, that one doesn't really matter very much because, if I do this a lot, then I'm going to get a little bit more accurate conversion toward theoretical mean and standard deviation. And what is actually changing those theoretical mean and the standard deviation? It's actually coming from that 20 rolls. And indeed, that's how we change it. Sigma over square root of n, or in this case, this standard deviation, individual standard deviation, over square root of 20, because we are doing it with 20 rolls. And the standard deviation of samples is actually hovering around here. Let's run it again. Run it again, run it again. Yes, it's hovering around 0.38 something. While the individual, that's hovering around 1.707 something. See the difference here? The punchline is this. Whether you take mean of means or mean of the samples, the mean will not change. It will stay the same. The standard deviation, on the other hand, well, this is for individual, and this one, or sigma over square root of n, is going to be for standard deviation of samples. So standard deviation of sample means. And that's going to be sigma over square root of n. And indeed, that's going to be the formula that we are going to be using. Do you understand this simulated experiment exercise? I hope I did an okay job explaining this. It's very, very tricky issue. In terms of problem solving, it's not much because there's one formula to memorize, sigma over square root of n. And indeed, we're going to use this for all those problems. But to understand the concept behind it is tricky because we have repetition of repetition and mean of means, and the standard deviation of means are confusing. By the way, if you're interested in the coding itself, it's not too bad, just based upon the random number generation. Just random number generator. Repeat 20 times and then repeat that repetition 100 times. So that's just simulated rolls of 2,000 dice. All right, we went through the hard part. Now we have a couple more examples about some other sample statistics, but they're de-emphasized in gray, which means they're not that important. So I'm going to talk about those in a separate video just for fun. Let's go directly over to 1.5. You see, we talked about mean of means and standard deviation of means, or sampling distribution of sample means, mean of 20, and in that particular case. Well, let's explore that, this time with visualization. Okay, here we go. Roll 4 dice 100 times and record the sum and the average. Previously, record it's the same as rolling 20 dice, but for visualization purpose, it's too much. 4 dice was sufficient, and as you can see, sufficiently complicated. Look at the blue histogram here. That's for the sum. The smallest possible number I'm going to get is 4. The lowest is going to be 1. 1, 1, 1, 1. That's going to be 4. And then the largest possible is going to be 24. 6, 6, 6, 6. And then we have this kind of distribution for this particular 100 rolls. And then this is the mean, average. So divide by 4, so we get the average. This picture and that picture are completely the same except for scaling, because the only thing was the scaling by dividing by 4. So look at down here, from 1 to 24, I mean 4 to 24, here 1 to 6, that's about it. Frequency in the y coordinate, they remain the same. But then again, do you see any pattern? Run it again, and any other pattern? Not really, I don't know about you, but I cannot really see anything. So let's increase this so that maybe I can see some pattern behind the probability distribution of this sampling distribution of sample means. And what do you see? You see a very nice normal behavior. And that's for the sampling distribution of sample sums. And this one is for sampling distribution of sample means. So you see, 4 dice, add them all up, and 4 dice, add them all up and divide by 4 for the mean. And how do they differ? Just scaling. So no difference except for scaling, so there's no reason to study sum. It's usually better to just go ahead with means all the time, which we're going to do. Here's another example and another visualization. Choose 5 integers from 0 to 20 a number of times and record the sum and the average. This is the sum, that's the average. And let's see, 5 numbers, if they're all 0, that's the minimum. If they're all 20, then that's got to be 100. That's the maximum. And we have distribution like that. And then this one, dividing by 5, we have from 0 to 20. Now run it again. Run it again. Do you see any pattern formation? No, not really. So let's repeat this a million times. What do you get? Again, you're going to see a nice normal pattern. See? Sampling distribution of sample sums and a sampling distribution of sample means. They are identical, of course, because the only difference is scaling by division 5, dividing by 5. So we went through the sampling distribution of sample means through some simulated exercises or simulated experiments, and then got the idea of mean of means and standard deviation of means. And then we did some visualization. Both are pointing toward the normal approximation, and that's something we are going to study in section 2 and section 3.